17 elements silently power every smartphone, jet, and wind turbine, far more common than gold, yet nearly impossible to replace. Rare earths are the unseen backbone of our digital dreams and clean energy hopes, with demand set to soar 600%. But what if the entire world's supply rests in the hands of a few? The real tech gold rush isn't about scarcity, it's about who controls tomorrow. A small black rock pulled from the ground in Ytterby, Sweden in 1788 set off a scientific puzzle that still shapes our world. That rock contained elements with atomic numbers 21, 39, and 57 through 71, what would become known as the rare earths. Their name is misleading. Cerium, for example, is more abundant in Earth's crust than copper. Almost all rare earths, except for promethium, outnumber silver, gold, or platinum in nature. The real challenge isn't finding them, it's separating them. Rare earths hide inside minerals, locked together in ways that make extraction and purification a chemical marathon. Their power comes from a quirk of atomic structure, F-electrons. Tucked away in a shell just beneath the surface, these electrons give rare earths their remarkable magnetic and glowing abilities. This single trait makes them essential for high-efficiency magnets, lasers, and phosphors. As Dr. Mira Lin, a materials chemist, explains, these F-electrons are the reason your phone vibrates, your car's motor spins quietly, and wind turbines turn energy into power. Rare earths are everywhere, yet almost invisible, an indispensable thread in the fabric of modern life. The leap from the 30-ton ENIAC computer to a smartphone that slips into a pocket was powered by a quiet revolution in materials. Rare earth magnets, small enough to fit on the tip of a finger, replaced bulky components and made modern electronics possible. The numbers tell the story. Over the past 15 years, global demand for rare earth elements has doubled, and the International Energy Agency projects that by 2030, demand could reach 280,000 tons a year. In 2009, experts warned of a looming shortfall, 40,000 metric tons annually, unless new sources were found. The pressure isn't just on consumer gadgets. In defense, the stakes rise dramatically. According to Colonel James Keller, a single F-35 fighter jet relies on significant quantities of rare earths, vital for its radar, targeting, and stealth systems. An Arleigh Burke-class destroyer uses thousands of pounds, while a Virginia-class submarine needs even more. The Pentagon's own releases highlight how dependent these platforms are on materials that can only be sourced from a handful of places. Every new device and every new weapon adds to a supply chain already stretched thin, making reliable access to rare earths a matter of both convenience and national security. Wind turbines tower over fields and coastlines, spinning on the strength of magnets made from neodymium, praseodymium, dysprosium, and terbium. These rare earth elements are the backbone of direct drive generators, prized for their ability to produce strong, lightweight magnets that keep blades turning even in low wind. The growth is staggering. Global demand for neodymium alone is projected to climb 48% by 2050, yet by 2030, the world could face a supply shortfall of 250%. Praseodymium isn't far behind, with a projected gap of 175%. Electric vehicles carry their own mineral hunger. The batteries that power them rely on lanthanum-based alloys, with each car requiring up to 15 kilograms of lanthanum just for the anode. The total mineral load for a single ETV can reach 200 kilograms, 6 times more than a traditional car. As Elena Garcia, an engineer specializing in sustainable transport, points out, every step toward zero-carbon technology tightens the squeeze on rare earth supply chains. The push for green energy is accelerating, but so is the race to secure the materials that make it possible. In 1994, China produced just over 31,000 metric tons of rare earth oxides, enough to make it a player, but not yet the world's supplier. Over the next 3 decades, that output ballooned to 270,000 metric tons by 2024. The numbers alone tell part of the story. Today, China is responsible for about 69% of all rare earth mining and nearly 90% of global processing. For the heaviest and most valuable rare earths, the figure is closer to 99%. Professor Wei Zhang, a policy analyst based in Beijing, describes how this dominance was built on purpose. The Chinese government offered loans, tax breaks, and state support to rare earth miners and processors, absorbing losses that would have bankrupted private firms elsewhere. Environmental regulations were often overlooked, and local protests carried little weight. The result? A vast industrial complex stretching from Bayan Obo's open pits to the chemical plants of Bio2, where tailing ponds seeped into the groundwater and the air hung heavy with acid mist. Meanwhile, the world's previous leader, Mountain Pass in California, faded into the background. As Chinese exports grew, prices crashed. The American mine, unable to compete with cheap Chinese supply and facing tighter environmental rules, shut down in 2002. By the early 2000s, China had captured not just the mining of rare earths, but the far more technical and lucrative business of separating and refining them, a choke point that left other nations dependent on Chinese processing for everything from smartphones to missile guidance systems. On September 7th, 2010, a Chinese fishing boat collided with two Japanese Coast Guard vessels near the disputed Senkaku Islands. The arrest of the Chinese captain set off a diplomatic standoff, but the real shock came days later. China quietly halted rare earth exports to Japan, which at the time relied on China for nearly 90% of its supply. Hiroshi Tanaka, an executive at a major Japanese electronics firm, remembers the panic on factory floors as shipments stopped and inventories vanished. Within weeks, the price of key rare earth oxides surged, some rising by a factor of 10 over the previous year. The Japanese government responded with urgency, approving a 100 billion yen budget, about $730 million, to secure alternative sources, launch recycling initiatives, and stockpile materials. Companies scrambled to redesign products and sign new contracts in Vietnam, Australia, and even Kazakhstan, but the shortfall was impossible to fill overnight. The embargo lasted 2 months, but its impact rippled for years. Manufacturers faced higher costs, and global markets learned just how quickly a supply chain could turn into a geopolitical weapon. Senator Laura Mendoza, a member of the U.S. Senate Committee on Energy and Natural Resources, later pointed out that Japan's experience was a warning for every advanced economy. She argued that no amount of stockpiling or recycling could erase the fundamental vulnerability. Nearly all rare earth processing still happened in China. By 2025, the pattern repeated itself. China imposed new export controls on 12 rare earth metals and refining equipment, citing national security. The West responded with tariffs and new partnerships, but the numbers told a sobering story. Even with billions invested in alternative supply chains, Benchmark Mineral Intelligence projected that by 2030, Western countries would still depend on China for 91% of their heavy rare earth needs. For every 1,000 tons of magnets produced in the United States, China turned out 300 times that amount. The pattern was clear. Each embargo, each policy change, each price shock only deepened the race for alternatives, but the finish line kept moving further away. Building a secure, rare earth supply means more than opening a few new mines. According to Dr. Mira Lin, the world would need 384 new mining projects by 2035 just to meet projected demand for minerals like graphite, lithium, nickel, and cobalt. Each new mine faces years of permitting, environmental review, and construction, often a decade or more before a single ton is shipped. In contrast, recycling rare earths from discarded electronics and electric motors is gaining momentum. The global rare earth recycling market is valued at $635 million and is growing at nearly 6% a year. With the right investment and infrastructure, recycling could supply up to a quarter of the world's rare earth needs by 2035. This approach promises faster results, lower environmental costs, and a crucial buffer against supply shocks. But scaling up remains a technical and logistical challenge. Laboratories from Tokyo to Boston are racing to find substitutes for rare earth magnets. Iron nitride alloys, manganese bismuth compounds, and even graphene-based conductors are showing early promise in prototypes, offering magnetic performance without the same supply chain risk. Yet none have matched the efficiency or durability of neodymium iron boron at scale. Governments are stepping in with tax incentives, direct funding, and procurement guarantees to accelerate the research. Senator Mendoza has pushed for a national policy toolkit that includes grants for alternative magnet research and development, mandatory recycling targets, and public-private partnerships to commercialize breakthroughs. The stakes are clear. Whoever masters the next generation of magnet technology could reshape the world's balance of power, loosening the grip of a single supplier and opening new paths for clean energy and defense. The race is far from over, but for the first time in decades, the outcome is not predetermined. Right now, every digital leap and green promise depends on minerals controlled by a single nation. As global demand surges, supply chains tighten, and alliances shift, the world faces a choice: diversify or risk progress held hostage. The next tech revolution won't just be engineered, it will be mined.